Hello students, welcome to the series of lectures on digital speech processing. So in this video, I am going to explain about the classroom discussion topic, that is short time average magnitude difference. So in the previous video, we have completed the autocorrelation function, so which is an alternative. So this topic, which is an alternative to the autocorrelation function. Okay, so let's get started with this. So this is a lecture learning outcome. On completion of this lecture, you will be able to illustrate the short-term average magnitude difference function. That means how we need to understand the mathematical expression, okay, and what is the main objective of this average magnitude difference function. So is there any difference between the autocorrelation function and this function, and what are the application of this average magnitude difference function? Also, we can easily get a knowledge from this video. All right. So as I already mentioned to you, that is it is an alternative to the autocorrelation function. So the main difference, it computes the difference between the signal and the time shifted version of the itself. Okay, so it's pretty much simple for us to understand, because when you see the autocorrelation mathematical expression, so here you will be having x of k into x of n plus k. So let me take the pen. Right, so this is the speech signal, for instance, okay, and this is the shifted version of the speech signal by k samples, okay. But in the autocorrelation function, here there is a multiplication instead of the subtraction. There is a multiplication. That is only the difference. But where in the case of here, you'll be having the x of k minus the x of n plus k, and then we are taking the absolute values. We are taking the absolute values. So what you need to understand, for instance, if I plot the signal like this, for instance, okay, so normal sinusoidal signal I'm going to be drawing. So let me take, this is the sample version of this sinusoidal signal like this, okay, and for instance, if you have this one, okay, and if you take this sample and if you take this sample, okay, because if you take the k is equals to 0, this is only, you are going to be taking the same first sample. But here, when you take a k equal to 1, so x of n plus k, and this sample you are taking the subtraction, and similarly this sample and this sample you are taking the subtraction, and this sample and this sample you are taking the subtraction. Okay, so that means what you need to understand here is that we are going to be converting the analog signal into the sample version, and there we are going to be having the subtraction from one sample to the another sample. Okay, and we are taking the summation of all the values. So there we are going to be seeing here the expression should be like this. The summation we are going to be taking from n equal to 0 to n minus 1 minus k, and we are taking 1 over n. So this is an average. Okay, we can get the average of that difference function. So ds of k is it dx of k or ds of k, whatever. So sometimes I can refer this as the s of k or s of n plus k or x of k, whatever, because when it comes to the speech signal, I can refer that as a s of k. Okay, we can designate with a mathematical expression, the signal should be the s of k. Okay, so this is a main important observation we are going to be considering here, is that so it computes the difference between the signal and a time shifted version of itself. Okay, but while autocorrelation have the peaks at maximum, which is also very important point I have mentioned in this slide. So when you see the autocorrelation function, okay, the curve, the plot of autocorrelation function, which have the peaks at the maximum. So similarly, there will be valleys in the average magnitude difference function. That is only the difference. Okay, when you want to compute the autocorrelation function, we know the mathematical expression and we also know how to compute that. Okay, we'll be having, if you want to plot that, we'll be having the autocorrelation function peaks will be maximum. But when it comes to the average magnitude difference function, we'll be having the valleys, okay, the deeps. Okay, the deep valleys will be getting. Okay. Alright, so this is a block diagram of the short time average magnitude difference function. Okay, so here we clearly mentioned this is the speech signal SF, and I clearly mentioned that sometimes I may refer to this as a speech signal as S of n. So S of n is directly given here, and another s of n minus k delayed by this s of n is delayed by k samples. So therefore you'll be getting s of n minus k. This is one more input to the subtraction. Okay, so now here you'll be getting s of n minus s of n minus k. Okay, so we can also refer this as minus, whatever it could be, k should be positive or negative. Okay, so s of n minus k, and we are taking the absolute. Okay, if we want to have any negative values, and we are taking that into positive by taking the absolute or the magnitude value for that. Okay, so there is a magnitude here, and then we'll be having to the summation. Okay, so and if you substitute k equal to 0 and k equal to 1, k equal to 2, like that, so many values that we are going to be having, in all the values we are going to be taking as a summation. Okay, and once it reaches the value n, okay, so this switch is going to be closed. Okay, because the maximum range of n should be 0 to n minus 1. That means n samples will be there. So this switch will be closed automatically when n is equals to n, and then we are going to be taking the summation and then 1 upon n, so which is an average. So at the end we'll be having the d of k. Okay, that is a magnitude, average magnitude difference function that we'll be getting. Okay, now when it comes to the short time, okay, this is a simple scenario how we can see the definition of the average magnitude difference function. Now let us focus our discussion with respect to the short time, because we are interested toward the short time parameters. In the time domain processing of the speech signals, we talked about in the so many videos, like so what is the short time energy, short time zero crossing rate, so like the short time autocorrelation function. Now in this video we are going to be able to see the short time average magnitude difference function. Alright, so the periodic signals of the period p, the difference function should be like d of n equal to x of n minus x of n minus k, just before we already seen, and that will be approximately 0 for k equal to 0, plus or minus p, plus or minus 2p. So this p refers to the pitch period. Okay, so this function will be approximately 0 for k equal to 0, and for k equal to 1 pitch period, and for k equal to twice of the pitch period, or k equal to thrice of the pitch period, like that. But for the realistic speech signal, the d of n will be small at k equal to p, but not 0. Okay, so ideally speaking, that is completely 0, but practically we'll be having the, because the speech signal is not stationary, it is a quasi-periodic signal. Okay, it is nearly periodic, but is not exactly, so it is a quasi-periodic signal. So therefore, for the realistic speech signal, this d of n will be small value. So based on this reasoning, the short time average magnitude difference function is defined as like this. Okay, this is also very obvious to us, because we know the definition of the average magnitude difference function, and for each and every signal we are going to be applying the windows. Okay, when it is rectangular window, how the process it could be, that we already aware. And if it is a Hamming window and then Hanning window, whatever the window that you are going to be applying to this speech signal, then we are going to be having the complete speech signal we are dividing into the frames, and from there we are calculating the difference function. That's all. Okay, so where w1 of m and w2 of m being the rectangular windows, and if both are same length, then that is similar to the short time autocorrelation function. Okay, whereas if w2 of m is longer than the w1 of m, then this gamma n of k, which is similar to the modified short time autocorrelation function. So in fact it can be shown that excuse me, so this kind of expression we are going to be witnessing if you want to apply any window technique to the speech signal. Okay, and this autocorrelation function and then modified short time autocorrelation function, and the way how we are going to be taking the length of the video that should be depends upon that. Okay, so in fact it can be shown that, so this gamma n of k equal to root 2 beta of k times of rn of 0 minus rn of k whole to the power of 1 by 2. So where beta of k, which varies between the 0.6 and 1 for the different segments of the speech. Okay, so that way we need to understand. Alright, so these are some pictorial representation we can easily understood here, is that when we want to plot the lag k versus the absolute value, and we will be having the dips. Okay, The first two plots which are refers to the voiced signal, and the third figure which is the unvoiced. Okay, and when you refer to the first figure, there are dips will be there. So this is the one dip, this is a valleys. So whereas in the case of the autocorrelation function, I clearly mentioned to you before the slide, in the before slide, what we have talked about is that when you want to see the autocorrelation function, we'll be having the peaks, but when you want to see the magnitude difference function, we'll be having the values. That's all the difference. And similarly here also there is a deep valley here there, and there is a dip valley here is there, and here also there. Okay, so this is a voice signal, and we are interested to calculate the pitch period estimation. Okay, so from here to here, the distance between these two values is nothing but one period. I can call this as the pitch period P, and here also I can call the pitch period is P, and the distance between these two is also one more period we are going to be taken into consideration. Okay, so this is the way how we are going to be estimating. Okay, so this magnitude difference function is also useful for estimating the pitch period. Okay, and pitch period estimation, that is it is makes sense to us when it is voiced signal, but not for the unvoiced. For unvoiced, we are not going to be calculating any pitch period. Please understand. Okay, thank you students, thank you for watching this video.